Hello, it's James from XRobots.co.uk. This is part 9 of my 3D printed R2-D2 style droid, which is in fact an R6 droid, hence its nice head shape and the orange parts. So in the previous episodes I've built this whole thing with 3D printing. I've had it driving around with its head spinning. It's controlled with a standard radio controlled transmitter and receiver and some normal electronic speed controls like the ones you'd have in a radio controlled car. So one of the features of those is they've got braking, which means that if you immediately go in the opposite direction it stops the motor dead, and also they don't go backwards as fast as they go forward, which is fine for driving the wheels but a bit annoying for turning the head, so that's probably going to get replaced. The other issue is that I've basically got these channels on one stick, and I've got an electronic speed control on each receiving channel, which means I have to push the stick kind of diagonally to drive forward. So today we're going to try and permanently fit the electronics in. Previously they were all attached with blue tape and hanging out to the back. We're going to try and route the wires nicely through the legs and mount the batteries properly. We're also going to have a look at some Arduino programming to do the servo mixing, which means I'll be able to simply push the stick forward to drive forward and left and right to drive left and right, which will hopefully make me a better driver. Alright, so here is an Arduino. This is an Arduino Uno, which is the reference design for Arduino. And this is a board that I'm going to use to do the servo mixing and other things. There's probably going to be several of these in the Droid. So I'm hoping in the future to add artificial intelligence with some vision recognition. So for now I'm going to dedicate this one board to driving and probably turning the head, which will be the main functions where it reacts to vision, and then I'll have other features in this droid, so it's going to be packed with lights and sounds and lots of gadgets that pop out from every panel. The other thing about this droid is that it's never going to have its skins on, so all the electronics and all the mechanics are going to be visible, so it's a real hacker's droid. So for that reason I'm going to be mounting the Arduinos in the panels so that you can see them. In fact, there are some features that go in here called utility arms, so this is going to go around the back. But first of all I need to mount a bracket for it. In fact, I'm going to make a bracket that holds two of them. Here are my Arduinos mounted on the mount there, and that fits obviously vertically and goes in the back of the droid, and I've got some flat surfaces to acetone weld this in. I've designed this thing so I can run the wires which go onto the inputs and outputs here on these pins. They can neatly run through those holes and I can get some cable management going. So Arduino is an open source platform. The hardware is open source so people can make compatibles and make clones and things like that. The software environment is free and open source. And that means lots of people have built modules for Arduino, so I've got some Adafruit NeoPixel rings here, and also an Adafruit soundboard which is going to go in the droid later. That's a 16 meg soundboard that will play sounds, and you can communicate it with it either by putting switches on the pins or by sending serial data to it. And these items have Arduino libraries which makes them really easy to program, so someone's already done the hard work. Similarly, there are shields that go on Arduino, which is another board that plugs in on top. And you can get those for various things, including Bluetooth and Wi-Fi, sound playing, and all sorts of modules. And lots of manufacturers make accessories for Arduino because it is open and it's very easy to make modules. So I've never used an Arduino before in any of my projects, and this is the first time, but I didn't find it too bad. So let's see what we're going to do with the servo mixing. So this is the Arduino programming environment. I'm using Arduino 1.0.5, which isn't the latest. The latest is 1.0.6 at the time of recording, but this one works perfectly well. So I mentioned there are some third-party libraries that have been written for interfacing with hardware, and one of those is the servo library. And all of the equipment I'm using, it runs with radio control servos, so of course I'm using a standard radio control transmitter and receiver that would normally run a radio control servo, and compatible devices like the electronic speed controls which run off servo PWM. So the first thing I've done here is include that library, and I've also attached two servos to it, and that's the command to do so. I've declared some variables here, essentially two input channels, two output variables, and also a difference value. So what we need to do is basically take servo values and we need to output them to two variables to the electronic speed controllers. And when we steer, we want one channel to the input channel to affect both output channels. So essentially it takes a number away from one motor and adds it to the other, so the droid goes round in a circle. So and the way we're going to do that is by basically reading the servos and working out the maths. So we've got the commands here to attach the servos. So these are physical pins. So the outputs that drive our electronic speed controllers are on pins 10 and 11, which are PWM pins, and our inputs, which come from the radio control receiver, are on channel pins 5 and 6. So I've put a note here to wire to actual channel 2 and actual channel 1 on the radio control receiver. One will be for the throttle and one will be for the steering. So first of all, we read them in. So we're reading in the channel 1 and 2 variables, and those typically vary between 11 and 1900. If you read this and monitor it with the serial port, those are the values you get. So the 25,000 there is the timeout, and 5 and 6 are the pins. The next command is the map command, and map will scale the variable. So it's saying take that channel 1 variable, which varies between 1100 and 1900, and scale it down between 70 and 130, and that's for the throttle, and then do the same for the steering. So that's 0 to 200. The next thing in line there is to constrain the values. So basically we're going to be adding these together, and we don't want them to overflow and get too big. So with Arduino variables, the value of the variable wrap round. So if you go over a number, it will wrap round back to 0 again in this case, which won't be very helpful, because it means if we drive too fast forward, suddenly the motors will go into reverse. So since I'm adding numbers to variables and taking them away, that's possible. So we're going to constrain them to some values, and we're constraining both variables between 10 and 190. Now the electronic speed controller likes to see a value of 100 as its midpoint on the output. And it won't actually initialize until it sees that value. So that's why I'm reading the variables here, pivoting around a point of 100. So 70 is 30 less than 100, and 130 of course is a 30 more, and this one is 0 to 200. So it means that both of these get scaled so that they start with roughly a value of 100 on the output to start with, and again they're constrained around that 100 as a midpoint. So then we've got our difference variable, and that takes the steering channel, channel 2, and takes away 100. So that gives us a difference from that midpoint, so that we can see how far we're steering. And the next command again uses map to go and scale that between a value of 0 and 65. Now I may mess around with these values to fine tune the driving when I've installed this in the Droid, and I'm going to be publishing this code as open source along with the CAD files. Have a look at the part 7a where I announce where you can download them. So you may find these values are slightly different if you have a look at this code in the future. And then we're outputting those values. So simply what we're doing is on the first motor we're taking the channel 1 variable and adding the difference, and on the other motor we're taking it and taking away the difference, which basically means that one motor will speed up and one will slow down as we steer. And then we do servo write to write those values out to the output pins 10 and 11, which we had at the beginning, which then plug into the electronic speed controller. I've programmed my Arduino here. You can see it's plugged in with USB and its green light is on. That will need powering in the Droid, and I'm probably going to power it from a USB boost adapter for now, but it will actually take up to, I think it's 6 to 20 volts on the V-in pin, so I can power that from a LiPo at some point. So here is my radio control receiver, which is this little module which has got an aerial on and receives from the transmitter. The servo is normally attached to those pins, and a radio control servo looks like this, which has a connector on with 3 wires. Red and black are power, which is typically up to 6 volts, and the white one is the PWM signal, which has that value typically between 0 and 255, which will make the servo turn. The servo probably won't turn to that value though. Normally you need something like sort of 70 to 200 or something like that. In fact, in this case I've been plugging the electronic speed controller into the radio control receiver, so that again has the same connector. The battery connects to here and the motor goes on here. So that's how it was connected, but now what we're going to do is put the Arduino in the middle, so it reads the values from the radio control receiver and outputs them to the electronic speed controller. And in fact we've got 2 electronic speed controllers, one for each wheel to attach. So we need to put all that inside the Droid and route all the cables around, so let's have a look at that. This is the back of the Droid, and the Arduinos are wedged in there. I haven't acetone welded this plate in, but I will do eventually. So to attach wires to the Arduinos, they've basically got these strips which have got sockets on, and you can buy these things on eBay quite cheaply, which this one happens to have pins on one end and sockets on the other, which is quite useful. So you can tear off a couple of these. I've got one here that's been made shorter, so that would easily plug into some of the Arduino pins and plug into, in this case, the radio control receiver, which is going to be mounted on the other side here eventually, and obviously the sockets plug straight into that. So that would work pretty well, and we could do all of it like that. The only slight scepticism is that these stick straight out, which is going to cause me a bit of an issue with transporting the Droid, and also I'm not particularly sure they're that secure, because these are individual pieces of plastic. So what I'm in fact going to do is use rows of pin strip, which is this stuff. This one is a right angle pin strip, and I can stick, you can snap these off to make them shorter, and then I can stick a whole row into there, and because they're all joined together it's much more secure, and also the pins are slightly longer. So I've in fact already done that. I don't know if you can just see, I've torn off a strip and stuck them in there where we need them. So the plan is to actually solder individual wires to each one of these and put heat shrink sleeving round, which is sleeving that shrinks when you heat it to make it nice and tight. Plug in a whole row, obviously not all of them will be connected, but I can use those in the future, and then basically cut off the wires on this end and solder them onto the appropriate place and run this off to my radio control receiver. So as well as that, I need to run some output wires and run those down the legs, which we'll have a look at in a moment. But for now I need to solder that up. This is going to temporarily float around on this side. Eventually I'll have another mounting plate for this and some other boards. I printed these little clips, which are again in white ABS, and these are to put the cables in so I can route them around the body of R2-D2. So these will just get acetone welded to the inside of the panels, and then I can run all my cables along inside them so they're nice and neat and tidy. Getting those wires attached to my pin strips, so I'm basically soldering them directly onto the right angle pin strip that's plugged into the Arduino, and then putting sleeving on, which you put onto the cable and heat with a soldering iron or a flame, and it shrinks nicely around the connector there to make a strain relief and make sure nothing else shorts out. So I just need to attach the rest of the wires. For the input, I've got the power from the 5V out on the Arduino actually powering the radio control receiver, and then I'll be running some longer wires off which go down the legs. Got my Arduinos in there and all the wires attached, and I've put this extra board in here which is holding the radio control receiver. It's also got 4 screws which are to mount another module, which hopefully I'll cover later in this video. So basically we've got wires each side which are going to go off down the legs. So the plan is, we just look in the top, hopefully you can see 2 bits of studding, and those bits of studding come all the way out, and those are the bits of studding that hold the legs, the feet parallel. So basically the idea is to attach the wires for each foot signal for the PWMs to drive the electronic speed controllers to those. I'm just waiting for some suitable spade terminals to arrive. Run the wires all the way down the leg. I left a hole in the foot. Don't know if you can see, but if I poke my finger through it, you probably can. It's just there. Comes out the other side, and then we're going to run the wires down into the feet. At the moment we've got nowhere to actually mount the batteries though. I previously blue taped them in there, and we've got these motor controllers to mount as well. And I've also put together some voltage monitors. I got these little modules off eBay, so if we plug that into a battery, it'll tell you that it's currently 11.4 volts, which is rather good. And I've put inline connectors so I can connect that to the speed controller, and these are going to mount in the back of the battery boxes that should belong in there and hold all of this lot. So we better get those printed out, and then we can finish mounting all of the electronics. Here are my battery box assemblies, which go on the inside of the feet and fictionally hold batteries, but in fact in this case they will hold the batteries. So on each one I've got a little pocket there that the battery fits into. So I've got that one in there, and I've made them big enough to hold a 5 amp hour LiPo as well, so I had to look at the dimensions of the typical sizes. So that's a bit loose in there. This is a 2 amp hour one, but it will hold a bigger battery. And if I connect this up here, then we've got the little battery monitor in the back there telling me the voltage. I've got my signal cable that comes in here for the wire that runs down the leg from the Arduino, and the bullet connectors there to go to the actual motor, and the motor controller's fixed in there as well. And I've got the little switch there that turns it on, so you should be able to hopefully see its little light. So there we go, and those mount on the inside of the feet. Now because I made my legs too narrow, these don't fit in between the body, so I've put this cutout, so in fact this overlaps the bit of the foot. But then I found the caster binds on this, so I've had to cut the corner off. So there's quite a few knock-on issues there from making the legs too narrow. So we'll fit those on and see how they look, but hopefully, mostly, we'll see them from the front, which is absolutely fine. So my battery boxes are installed. Those are acetone welded onto the feet, so they're nice and strong, and they've got the batteries connected, and they've got the display on each one telling me the voltage. So I'm currently powering the 5 volt electronics from this USB boost adapter. Eventually I'll have another LiPo in the body which will do lots of things, including turning the head, but it'll also power 5 volt electronics like lighting and servos. I'll be feeding 12 volts into the Arduinos, but I don't want to use the 5 volt feed off those to power all the 5 volt stuff because the regulators on board are only small. So if I turn on my remote control transmitter, you should see the little light comes on in the receiver, and if I turn on the motor controllers, each one gives me those 3 beeps and a long beep, which tells me they're happy. So now, should be able to drive, but I won't do that here. We'll put it on a smooth floor and see how well that Arduino servo mixing steering works. Right, we're all wired in and ready for a test of that differential driving system. So I've got my remote control transmitter here. So if I push forward now, it does go forward. And I've got braking, so I need to just double click backwards and I can go backwards. And now if I push to the left, it spins to the left, and right, it spins to the right. And obviously if I push forward and slightly to the left, it drives in a circle or the other way, and that's actually really quite responsive. So I only had to change one value on the Arduino code, which was the lower value for the constraint on driving, and that's because it doesn't go as fast backwards. The motor controllers are limited in speed backwards, which meant it was really sluggish. So I've just turned that value down, so now it goes backwards. Not quite as fast, but at a reasonable speed. So I can drive forwards and backwards, and it's not really sluggish. And obviously it still goes top speed for all the other functions. That's really quite easy to drive now. So lastly, we need to do something about that turning head, because we don't want the braking function of the motor controllers on that, and we really want it to turn in both directions at the same speed. To make the head turn, we're going to use a different type of motor controller. This is based around an L298 dual H-bridge chip, which is the big black thing stuck there with a heatsink. This is quite a common device, and these boards you can buy quite cheaply on eBay. So this will actually drive 2 motors, and it will drive each motor in either direction. This is quite good for 2-wheel robots. It'll only do 2 amps of current, so we can't use it to drive the wheels, but the head turning motor will be fine. So this is split into 2 halves. We've got 2 connectors, which are the blue connectors there for 2 motors. We're only going to use one of them, and we've got power connector here. We've also got some input pins. So for one channel we've got 2 pins, and the other 2 are for the other channel. And basically if we drive a signal into one pin, the motor will spin one way, and if we drive it into the next pin, the motor will turn the other way. And if we vary that voltage that goes in, or we use PWM out of the Arduino, we can control the speed. So that's slightly different to how the other motor controller works, which has a central position with a value of 100, and if it goes up, the motor will turns one way, and if the value goes down, it turns the other way. With this one, we need to make one pin 0 and the other pin have something on it to turn one way, and that pin be 0 and the other pin have something on it to turn the other way. So we need to do a bit of coding in Arduino. This is version 2 of my servo mixing code, which I'll also put up on my GitHub with the R2D2 CAD files. So what I've done in addition to the code I had last time is added a new variable here for the head turning input variable, and also 2 output variables that basically are for head turning and go out to the PWM driver. I've also assigned 2 additional output pins here, 5 and 6, and I've changed these pin assignments around since I last showed you the code, and that's because these are PWM pins, so I'm now using 2, 4 and 8 as inputs. So 8 is the input there, which is actually wired to channel 4 of the radio control receiver for head turning. So I'm, as before with the other servo channels, I'm reading in channel 8 here with the pulse in commands, and I'm also constraining it and mapping it. So I'm scaling it down from the value that we normally get from the receiver, and in this case I'm scaling it between 0 and 510 and also constraining it to those values. And 510 happens to be double 255, which is the maximum value that each PWM channel is expecting on the PWM board. To get the actual values that output to the PWM driver on H output 1 and H output 2, I've decided to assign a dead spot, so the head doesn't turn in one direction until the value out of 510 exceeds 280, and doesn't turn the other way until it's smaller than 230. And if it's neither of those, then both of the outputs are off so that the head doesn't turn at all. So in the first case, I've said that the channel 3 variable will have 255 taken away from it. So if it's right in the middle, it actually zeroes that value, which means that it swings about a point of 255. Similarly, to turn the other way, I've had 255 minus the channel 3 value. So that does exactly the same thing, but in reverse. So finally, I've added the additional analog writes, which are the PWM commands, to actually output the H output 1 value and the H output 2 value to pins 5 and 6, which are PWM pins on the Arduino, and those are wired to the PWM driver. There is my L298 board mounted on the left there, just under the radio control receiver, with the relevant wires wired to the Arduino. I'm still powering the 5 volts from the USB boost adapter, and I have an additional LiPo there which is powering the head motor. Eventually I'll have some proper 5 volt and 12 volt power distribution around the Droid, but for now we've got lots of crazy batteries everywhere. So obviously this works now, so if I turn the head stick, and my head turns at varying speeds with a nice dead spot in the middle. Which works quite well. So that's the end of another R2-D2 episode. Don't forget to check out part 7a to find out where you can get hold of the CAD files and all of the open source Arduino code for absolutely nothing. If you'd like to know how I fund my projects, then have a look at patreon.com/XRobots, which is my crowdfunding campaign. You can get access to some exclusive rewards, including a live broadcast with me.